Up to this point of mechanics, with motions, we ourselves controlled the accelerations which resulted. Today, we want to take a look at motions which nature provides us. And of all such motions, that of freely falling bodies is by far the most familiar to us, the most common experience of man. Now, I know you know all about the motion of freely falling bodies, but just to refresh our memory about the sort of things that can happen, let me take one of these three objects first on the table. Hold it up, drop it. Now let's take another one of these. We hold it up and drop it. Quite a different motion from the first, isn't it? Now we know very well that it's the effect of air resistance that's responsible for the difference in these two motions. In fact, the effect of the air can be widely different in different cases. For example, let's take a look at this third one. I hold this one up, let it go. You certainly see that all bodies do not fall alike. If we are to get at any law, if there is any law of physics underlying the motion of falling bodies, we'll have to do something about the air. Now, the simplest thing to do would be, in principle, to pump the room out or to do our experiments in an evacuated chamber. But this is awkward and clumsy, and we don't need to go that far. Let me show you how we can eliminate, or at least minimize, the effect of air resistance in the following way. Here is a book, and here is a sheet of paper. Let me start them at the same height and drop them at the same time. You see the book plummets straight down, and the paper just floats down. Now, if I'm going to reduce the effect of air resistance on this piece of paper, let me crumple it so it forms a more compact mass. And now let's watch what happens when I drop these two again. You see they fell much more nearly alike, and in fact, if I go still farther and crumple this into a very dense, compact wad, I think you'll see that by so doing, we have virtually eliminated the different effect of air resistance on the book and on the sheet of paper. Now, this is really a remarkable thing. Here, a sheet of paper, only one tiny fraction of all the sheets of paper which go to make up the book, plus the hard covers, perform identical motions in the absence of air resistance. But this remarkable fact is not confined only to a sheet of paper and a book. Any object, this pencil, this croquet ball, this lead brick, block of wood, cigarette lighter, comb, anything you imagine. If we let these bodies fall freely in vacuum, or what is the same thing, under such conditions that air resistance is negligible, they all fall with the same accelerated motion. During the past few weeks, we've learned that to accelerate a body, it takes a push or a pull. And when this push or pull is in the direction of motion, the force is related to the acceleration of the body by Newton's law of motion. F equals ma. You notice I've put a subscript I on the m, and this is to remind you that this mass is the inertial mass of the body, a dynamical property of matter. For the case of freely falling bodies, we already know the acceleration. Do we know anything about the left-hand side of this equation? The force F, which produces the acceleration of freely falling bodies. Yes. This force is the gravitational pull of the Earth on a freely falling body in the case where the air resistance is negligible. Earlier, we used this same gravitational pull of the Earth to establish a measure for another different property of matter. This property is the gravitational or chemical mass of a body. To do this, we used an equal arm balance, such as this. When the balance is in equilibrium, the gravitational pull on each of the bodies in the two pans is equal. And this establishes the equality of gravitational mass. Now, this equality does not depend on where we do the experiment. Equal gravitational masses will balance no matter where you do it. In this room, on the top of the mountain, even on the moon. Now, the actual gravitational force on a body depends on where you are. But in any case, this gravitational force is proportional to the gravitational mass of the body. If we write this proportionality in the form of an equation, it looks like this. Gravitational force is equal to a proportionality constant g times the gravitational mass of the body which is being pulled. This g is called the field strength of the gravitational field produced by the attracting body. It is the force per unit mass with which the attracting body pulls on any object. And it depends on the location of the object. It's smaller on the top of a mountain than it is in this room. The field intensity of the moon at its surface is only about 1/6 of the field intensity of the Earth at its surface. Now let's compare these two results. Here are two expressions equal to the same thing, the gravitational force. Therefore, they are equal to each other. There it is on a card. Now, little g, gravitational field strength, doesn't depend on the body. It's the same for all bodies. It depends only on the thing that does the attracting, not on the body that's being pulled. We have found out experimentally that the acceleration of freely falling bodies doesn't depend on which body falls. It's the same for all bodies. Therefore, no matter what body we're talking about, gravitational mass is proportional to inertial mass. And here it is written up. This is an amazing characteristic of matter. There's no reason beforehand why you should suspect that that property of matter, gravitational mass, which tells you how hard some other material body pulls on it gravitationally, should have anything to do with inertial mass, MI. That property of matter which tells you how much acceleration that body will get when you pull on it with any kind of force. Actually, if we use for both these masses, which are now proportional, the same unit, the standard kilogram, then the numerical values become equal, and we say that gravitational mass equals inertial mass. Now, this experimental equivalence between these two different properties of matter, gravitational property on one hand, inertial property on the other, is really the reason we use the same word mass for both these quantities. Now, what else can we learn by studying the motion of freely falling bodies? As long as we confine ourselves to looking at motions that are along a vertical line, whether we throw a body straight up or down or let it fall from rest, there's not a great deal more of interest. However, if we look at this motion of a falling body, here's a piece of chalk. There's a motion different from any we've met. It's motion in a curve, and this is the first time we study such motions. During this motion, the gravitational pull of the Earth is straight down. It has the same value at each point of the motion, and furthermore, the direction of motion is different from the downward direction of the force at every point. We now ask the following question. Does this downward gravitational pull of the Earth produce the same downward acceleration for the curved motion as it did for a body falling freely from rest? There's only one way you get an answer to such a question, and that is from experiment. Let's first try a simple experiment. Let me take a couple of coins, $50, place them at the edge of the table, one slightly behind the other. I will now flip these off the end of the table so that one coin will just fall over the edge and the other will be projected with a relatively large horizontal motion. I want you to listen for the sound when these two hit the floor. Here we go. One sound, not two. It took just as long for the coin which was projected horizontally to hit the floor as it did for the one which fell straight down. Now, this equality of the time of fall for both these coins suggests that maybe the vertical motions are identical at all instants of time. Let's do another experiment to see if this is really so. Instead of the two coins, I'm going to use these two balls, one of which is hanging here on a magnet, and the other I will project horizontally by sliding along this trough. Now, to make sure that they start at the same time, there is a switch here which will break the circuit holding the ball. And as you see, when this ball leaves the trough, just at the instant it starts falling, the other one falls. They start at the same height at the same time. We're now ready to do this experiment, and I want you to watch the vertical motion of both these balls and compare them as they fall. There you see the motion of the two balls, one projected horizontally, the other dropping from rest, and both starting to drop at the same time. Now, in order to see the details of these motions and to compare them, let's watch them in slow motion. Keep your eye on the vertical height of each ball at each instant of time. Now, to go one step, we're going to repeat this experiment and show you pictures of the position of each of these balls at equal time intervals. On each of these pictures, you see drawn a line tangent to the bottom surface of each of these falling balls. Each of these is horizontal. This means that in equal times, both bodies have fallen the same distance. Exactly. The vertical acceleration produced by the pull of the earth on each of these balls is exactly the same, although one is moving with a horizontal speed and the other is not. But there is more that we can get out of these pictures. If we look at the horizontal motion of the ball I projected and construct vertical lines tangent to this in each one of our still shots, we see that these vertical lines are equally spaced. This shows that the horizontal motion of the projectile was one of constant speed, unaffected by the vertical downward pull of the earth. Our general conclusion is then that the vertical accelerated motion of a freely falling body is unaffected by what goes on horizontally. And the uniform horizontal motion of a projected body does not depend at all on the fact that it simultaneously undergoes vertical acceleration. Now, using Newton's law of motion, we can find out something more about the nature of inertial mass. You notice I have added arrows over the force and the acceleration in this formula. The reason is that we have determined experimentally that force is a vector, and we know that acceleration is a vector from its definition. Now, what we have found out from our experiment is that the vector force and the vector acceleration are in the same direction no matter which way the body moves, no matter what the direction of motion is. And from this, we can conclude that this inertial mass, that quantity, does not depend on the relative direction of motion and force. This leads us to suspect that maybe the inertial mass doesn't depend on direction at all, that it has no directional properties. You can't prove this completely by just looking at falling body experiments, but other experiments do confirm this notion. Mass is a scalar quantity. Now, we found out something else in addition. You remember that the horizontal motion of a freely falling body was independent of the vertical motion. What happened vertically had nothing to do with what was happening horizontally. This is true in general about curved motions. The component of any motion in a fixed direction in space is independent of the component of motion at right angles to the first direction. This mutual independence of these two components of motion enables us to solve problems in a rather simple way, which otherwise would get somewhat involved and complicated. Let me take a simple example to show you how this goes. Imagine you're in a jungle hunting monkeys, and you come across one hanging from the limb of a tree. Now let's suppose that when you fire at this monkey, at the flash of your gun, he lets go and starts dropping. The problem is, where should you aim to ensure a hit? Now remember, you don't know how far you are from the monkey. He may be above or below you, and you have no idea what the muzzle speed of the bullet is which leaves your gun. Now let me show you how one uses the independence of vertical and horizontal motions to solve this apparently complicated problem. To make life easy, let's start with a simple case. Now first, let's consider the simple case where you and the monkey are at the same height. Suppose this represents the position of the gun, and this, the position of the monkey. If, for a minute, let's imagine that the force of gravity does not act, then you know very well how you should aim to hit the monkey. You aim horizontally, right at the monkey. The bullet travels in this straight line, and you hit the monkey. Now what happens in the real case where the earth pulls on both the bullet and the monkey? We know that the vertical motion produced by this downward pull is the same for both. The horizontal speed of the bullet determines how long it takes for the bullet to travel from the gun to the line of fall of the monkey. And in this time, the monkey falls, let's say, down to here. During this time, the bullet undergoes the same vertical motion as the monkey and will follow a path something like this, falling exactly the same distance, and we get a hit. So you see, for this simple case, the way to hit the monkey is to aim at it. How about the more complicated case where the monkey is not at the same level? Let's say he's above you. Let's take a look at this one. If, again, this represents the location of the gun, and this, the location of the monkey, hanging from the limb of the tree, you remember. Once again, if gravity were not acting, we would again aim at the monkey. The bullet would travel along the straight line, joining the gun and the monkey. Notice that in this case, the muzzle velocity of the bullet, which I'll represent by this vector v, has a horizontal component so. And this horizontal component determines how long it takes for the bullet to reach a vertical line drawn through the monkey. The vertical component of velocity, which is proportional to the horizontal component, ensures that the bullet will rise just exactly the right amount to cross this vertical line at the height that the monkey is. All right, what happens now in the real case? In the real case, you fire, the monkey starts falling. In a certain time, a time determined by this component of muzzle velocity and this distance, the monkey will fall to here. The bullet will no longer travel along this straight line, but will have a vertical downward acceleration exactly the same as that of the monkey. In the same time, then, the bullet will follow a path something like this and will end up below this point, which it would have reached without gravity, at a distance below it just exactly the same as the distance the monkey's following. So you still get a hit. The answer, then, is extremely simple. If you want to hit the monkey, you just aim at it. In fact, it's a lot easier to hit a target which starts falling from rest when you fire than it is to hit a stationary target. Now, does this really happen when you do an experiment? Well, we're not going to shoot a monkey, but we're going to do an experiment which does exactly the same sort of thing. This magnet and ball, which you've seen before, now represent the tree and the monkey. The gun can be adjusted to give different speeds and be aimed, as we will see. This is an old-fashioned crossbow made out of a leaf of an automobile spring. Here you see a pair of gun sights being mounted so that we can aim the gun properly. As you see, they are adjusted so that we aim the center of the ball. Now, we're sighting through these sights, and you see we aim at the center of the ball that represents the monkey hanging on the limb of the tree. To make sure the monkey starts falling when the gun's fired, we use this switch, very similar to the one we used before. Now, let's change the muzzle speed of our projectile. Move the monkey up. And there we are, hoisting the monkey, or pushing him up, rather, and attaching him to the limb of the tree, the magnet up near the ceiling. Here's the shot, and it's in slow motion so you can follow it. Are we going to make it? Now, once again, let's take another look at this. Watch closely. Now, what have we learned today? First, we learned that all bodies, no matter what they're constituted of, in the absence of air resistance, fall with identical accelerations. This equality of acceleration for all bodies led us to the conclusion that gravitational mass, that property of matter which tells you how hard the Earth pulls it, is identical with inertial mass, that property of matter which tells you how hard it is for any force whatsoever to change its velocity. Now, you know very well that this acceleration of a freely falling body is constant. But this is really unimportant. After all, it only tells you how small you are compared to the size of the Earth. Secondly, from experiments with projectiles, we found that the horizontal and vertical components of motion were independent one of the other. What happened in one direction did not depend on what was going on in the other direction. This experimental evidence lends support to the idea that Newton's law of motion is really a vector law, And it's a vector law in which force and acceleration are the vectors, and mass is a scalar. This scalar mass has no directional properties and does not depend in particular on the relative direction of motion and force. Now, in addition, this independence of component motions along fixed directions at right angles to each other allows us to solve certain complicated problems of curved motion rather simply. You simply take one component of the motion, make believe all the others aren't even there, solve for it. Do this for each component and combine the results by vector rules, and there's the answer. And finally, and this is by far the least important thing we've learned, you found out how to shoot monkeys.